Okay, great. Thank you, voice in the data center. So good morning and welcome back. Today, our focus will be continuing our conversation about probability, specifically how we think of data. And we will discuss, among other things, an interpretation of what various probabilistic summaries mean, as well as things that will help you build towards project number 2, which is out on the Canvas site. So to kind of warm everyone up, my 10-year-old, well, she kind of groans about it now, likes dad jokes, right? So I have a good one. Um, what do you call a company that makes okay products? No? I'm sorry? A satisfactory. Yeah, there we go. Thank you. Thank you. I got one laugh. All right. Thank you. All right. All right. So good morning. Here's another one. Why was 6 afraid of 7? What do you think? Because 7, 8, 9. Oh, you know that one. All right. All right. I have to think of some other ones, but not right now. All right. So good morning. Today we're going to continue on our conversation of random variables. But before we begin, the usual administrative bits, the reading has not changed. And again, I treat you like the adults you are. The deadlines are there to help you with pacing. And so I put a PDF for a book that's an open book. It's available for free because, again, I don't like to participate in the mild financial extortion that is the textbook racket. I believe in compensating authors for their work, but I try for opportunities to reduce costs for your textbooks as much as possible. In my class, at least, can't speak for colleagues across the university. But that being said, the reading, I won't read it off. It's there for you. Project number 1, the solution, or I should say a solution, not the solution, has been posted. We will take opportunity on Wednesday in the practical session to go over salient points in that solution file in Python. And I say a solution and not the solution because certainly there's more than one way to address this problem. Okay, on project number 2, I was a little bit late in getting this out. I had promised Friday night. I got it out, I think it was Saturday. There were some other issues I had to attend to. And it's an early peak. It's not due until a week from Tuesday. And we will certainly, on Wednesday in the practical session, talk about some of the visualization APIs, specifically matplotlib for Python. I won't cover Seaborn, but I hope on Wednesday, our conversation will give you enough bits for you to be confident to go off and look up Seaborn if you choose to, right? I'm not going to make Seaborn a part of the course, but Seaborn takes matplotlib types of constructs and makes it look a lot more visually pleasing, much prettier graphs, as well as the types of graphs are a little bit more extensive in Seaborn. Okay, any questions? No questions? And I have a big smudge right in the middle. Wear glasses. Pause. All right, no questions? No? All right, let me make sure the mic is still on, just because it makes it a little easier and I'm recording. Okay, let me hide this again. And let me make sure the clicker is going. Okay, so where we last left off, we talked about the key ingredients needed by a probability. We talked about trials, we talked about observations, and this last part, when can I see you again? And so with this, we built up a construct over all of the possible events that one can observe from a system, the so-called sample space omega. And we discussed how you use the numeracy of the objects or the possible events that you could possibly observe from a system. We use that cardinality in order to give us the tool for calculating this when can I see you again, the probability, which represents the proportion or the rate, as it were, of the number of times you're going to see a particular outcome over a large number of trials. And so a probability is an asymptotic construct because in practice, if you run a real trial, like rolling a die, you're not going to get 1/6 probability for a particular outcome unless you roll that die several times and record or do the accounting for the occurrence of that desired outcome. Okay. Any questions? Does that make sense? Jar your memory? All right. And so then we also extended this to the idea of a random variable. And this allows us to tie things that are measured out in the real world to this treatment for probabilistic description. And so we motivated this with the 3-coin flip system, as I'll call it. And the random variable, we said, was nothing more than a function that measures something over the base event or the raw event. Okay. And in this case, our function measured the number of heads outcomes over this 3 many flips in our coin flip system. And we took that and we did an accounting in our table of the probability associated with all of the outcomes collectively that our random variable X can take on. And so we said we could observe in 3 flips 0 many heads, 1 heads, 2 heads, or 3 many heads, each of which is associated with a probability per centum by the 100. And we list this out in a table, and we said collectively this table describes the behavior of this particular system. All right. Any questions? No? All right. And we called it our distribution because you can think of it as this probability handing out values, these proportions associated with each one of our outcomes that our random variable can take on. And so we said we can plot this, and along the horizontal axis, we have our sample space omega, all the possible observations. A synonym for that is the so-called support set. And depending on which problem stats book you use, they might use different terminologies for it. So I try as much as possible to give you these synonyms that you'll find in books and in the literature. But nonetheless, along the horizontal axis, we have our support set. And on the vertical axis, we have our probability. And so we can draw out these probabilities associated. And this is a graphical representation of the distribution depicted in the inset on the right in table form. And so what we're concerned about when we describe the data or aboutness or the data behavior of this particular system, we're less concerned about the individual probability mass points, and we're more concerned about the shape of this distribution. And as such, you take these mass points and you construct a graph, and you notice this particular graph, as the counts or the outcomes of random variable X increases, we start increasing in our probability. It remains level, and then we have a decrease at the high end for the outcomes for this random variable. Okay, any questions about this? No? So important is this graph, this visual representation, the envelope, that when we talk about the behavior of the underlying system, what we're really concerned about is the shape of this graph and not the individual values for the mass points distributed across the support set. Okay, any questions? That makes sense? Still pretty early? All right, I hear you. All right. And so we talked about this idea of probabilistic summaries. And the whole purpose of a probabilistic summary, and we're going to fill in more rigor on this idea of probabilistic summary and discuss how it describes aspects or important aspects of the shape of these distributions from their visual form. And so listing out a table can become cumbersome. Now, with something like the 3-coin flip system, it's pretty small, and I present that because it's easy to talk about. But you can imagine if we had 1,000 flips of the coin, that would be a much bigger table. And because these tables, these distributions, can be very, very large, it's not always convenient to list them out, and in some cases, to even visualize them. And I'll comment on that towards the end of today if we get to that point in the slides. Okay, any questions? No? So what these probabilistic summaries give you is a value, and this value, whether it's a big value, a small value, or something in between, tells you something about the shape of the distribution. Okay. Any questions? No? Make sense? Jar your memories? Okay. And so let's continue on with this idea of probabilistic averages. And I'm really hoping the coffee kicks in right about now. Often in practice, there are too many pieces of information in your distribution to practically write out the complete accounting of it, right? It's almost never done in purpose for real problems. And you can imagine if you're looking at a distribution over, for example, all of the values of pixels in, say, a high def image, right? That's 1920 by 1080 by two, let's see, by 256 cubed, right? That's a lot of different values that you'd have to list out in a table. It's practically impossible or not practical to list that out. So the solution is to write down a summary that describes aspects of the stochastic behavior. And the summary is precisely a description of the shape of the distribution. And you write it out so that readers can understand it. And so for part of your analysis for project 2, you'll be doing some simple summaries, probabilistic averages, for the SMB data. And I furnish for you a consolidated data file, which is the output of the solution for project number 1. Okay? All right, any questions? No? Makes sense? No? All right. And so the so-called summary statistics, and today we'll talk about the mean and the variance, and you can't talk about variance without talking about standard deviation. These are just two, but they're not the only ones, and we'll have opportunity to talk about what are called the higher order moments as part of this class later on in the semester. Okay? All right. And so expectation. Expectation, when we computed or played that gambling game in our last class meeting, what we were computing was the expectation. And you can think of expectation as asking the question, what do you expect or what do you believe from the data or from the distribution more correctly will happen on average? Now that average is not just a typical average that you understand from casual parlance, it's a probabilistic average. And so it was on purpose that we weighted each one of the outcomes, $2 you get, or minus $1 you get. It was on purpose that we weighted those values by the associated probability with the heads and the tails. Okay. Any questions? No? No questions? All right. And so this is a probabilistic average. And now that's my terminology because it kind of really is descriptive about how you calculate them. And this is our first probabilistic average. This is the mean, and in all of the cases, these probabilistic averages or these summaries, or so-called summary statistics, are given a Greek letter, which is a synonym for a procedure. And so when we say mu, we mean the mean. And oftentimes you'll see this other notation in functional form, E of x. The parameter is a random variable because that's the quantity for which we want to compute a probabilistic average. And you'll see it in parentheses. And everything in parentheses is going to appear in the expansion of the function that describes the procedure for this particular probabilistic average. Every time you see E of something, that something can be a random variable or it can be a function of a random variable. It doesn't matter. Either one, it's still an expectation, as it's called, or a probabilistic average. Any questions? No? All right. And so here, what we do, you'll notice inside this expression, we have a summation, and this summation iterates over all of the possible instantiations of this random variable. And so here, under the summation, you'll see a subscript x, and that means that we're going to evaluate a sum, and each of the terms in the sum is going to be one of those values that our random variable big X can return. So in case of the 3 coin flip system, little x would be 0. We evaluate this expression. Little x would be 1, then 2, then 3. And for each value that this random variable can take on from the support set, we're going to multiply that by a weight, which is the probability associated with that outcome. Okay. Any questions? Does that make sense? And so if we had, for example, E of random variable big X squared, inside of our expression for this probabilistic average, we'd have x squared, the value x quantity squared, and not just x. Okay? All right, any questions? No? All right. And so here we have probabilistic average, and I've gone ahead and I'll try this as much as possible to kind of mix up the notation a little bit to give you different examples of how different books and different pieces in the literature will express the same concept. In other expressions for the mean, we have E of x, that doesn't change, and this is a typo. Oh, you know what? I got ahead of myself. All right. Yes. All right. That's one of my waking up brain hiccups. And so let's go back. This is our expression. And in this expression, we have the probability P of x, and that is a probability associated with each one of the outcomes our random variable big X can take on. Now, of course, there's a special case of this. And that special case, is often used in real data problems where you have no idea and there's no way to estimate or make an educated guess from data what the correct probability should be. And in the case where we have what's called a uniform distribution or random system, meaning all of the probabilities associated with all of the outcomes of the random variable are the same. And so this is different from our 3-coin flip system, because for a 3-coin flip system, the outcome of 0 heads, 1 heads, 2 heads, and 3 heads, they were not equal. But for those systems where the outcomes of your random variable are all equiprobable, if we substitute in that equiprobable probability for big N many outcomes, we would have our expectation is E of x, and I have a typo here. It should say the ith instantiation or outcome of our variable times P of x, right? That P of x is missing. I go over the slides in the morning and I make additions, and I had a typo in that addition. And if we substitute for P of x, that equiprobable idea, we get 1 upon n as the probability associated with a particular outcome. And so we have here the sum of each outcome, the ith outcome, xi, times the probability of xi, which is 1 upon n. And because each term is multiplied in the sum by 1 upon n, we can factor that out. So we can bring our 1 upon n out of the summation. And if we expand it in a different form, we get exactly the average that you know casually. And so the average is nothing more than this expectation, the probabilistic average, under the assumption of equiprobable outcomes. Okay. Any questions? Does that make sense? All right. Yes. Yes. If it's not a loaded die, only if the random variable is just measuring the outcome of the die, because the random variable might be measuring something else over the raw die outcome. So if you roll the die, say 5 times, and you wanted to know, for example, the random variable is saying the number of heads is greater than half the rolls, right? So in that case, the thing you're computing the probability over is the random variable. And it all depends on what your random variable is measuring, because here we talk about the probability of a random variable, not the probability of a raw observation. Does that make sense? And so if your function, your random variable, was taking a coin flip and it was saying, what is the outcome of your flip, right? It's equal to heads or tails. That random variable choice, that measurement, that random variable has equiprobable probabilities. But if your random variable x was measuring the number of heads is greater than the number of flips over 2, that is not equiprobable. And so it's important, and I'm glad you asked that question, it's important to remember what the probability is being defined over, right? And so in this case, the random variable, it's trivial, saying what is the raw outcome? That's a type of function. You give it the outcome of a flip, it just returns it back to you. In this case, this version of the random variable, you give it a sequence of flips, and it's returning back the counts and seeing, oh, is it greater than half? Yes or no? Does that make sense? Okay, so I'm being very, very technical here because we're using this abstraction, this random variable idea, to allow us to make arbitrary measurements over outcomes. Because in the real world, you don't just measure things like individual coin flips. You measure functions over your observations. And so imagine if you had, for example, a Holter monitor. Holter monitor measures your heart rate, and if someone has AFib, arterial fibrillation, my wife's a nurse, so I asked her about this. You measure your heart rate over a period from weeks to maybe a month or two, and you wear this thing, you bring it home. Now, for heart rate, you want to know what your heart rhythm is, but more important than the raw outcome, the heart rhythm, is the change in heart rhythm, because what they're really concerned is that function, all right, that first derivative in time. And so using random variables, this idea of functions that you compute over observations is really, really important to make this work in the real world. Okay. Any other questions? Does that make sense? Okay. And so going forward, we're going to talk more about random variables and not raw outcomes for that reason. Okay. And so our expectation for the random assumption, equiprobable outcome for the random variable, is the same as the average as you know it. Okay. And so here, I forgot why I drew this graph. Oh, yes. Okay. I'm going to go through the intuition behind what this mean is doing. What does the mean mean? No pun intended. And so here we have our distribution. Along the horizontal axis, we have the outcomes of our random variable x. And this is sort of going back to ground it out to the 3 coin flip system. And so again, to remind you, for that example, our random variable is measuring the number of heads given 3 flips of a coin. And so here, horizontal axis, we have the outcome, 0 heads, 1 heads, 2 heads, 3 heads, and 3 flips. Along the vertical axis, we have probability. And so we draw the so-called mass points for our probability. And then we can imagine these mass points as weights. And because of acceleration due to gravity, these masses experience a weight. And so I draw these as vectors in the downward direction. And you notice those masses that are larger, they experience pull to gravity and they're heavier weight, and those vectors are longer, right? So bigger mass means higher weight. So you can imagine then, if you were to convert this into a physical example of a seesaw, and I'll use this to explain what this probabilistic average is doing. Now, I was born overseas, and so, growing up, learning colloquialism was always an interesting challenge. Someone would say, "What's up?" And I'm like, I don't know. Up there, I don't know what's up. And so I called it a teeter-totter, but this is a seesaw, so it won't make the assumption that you know what this is. And so it's a piece of playground equipment, and 2 people sit on the ends, and depending on the weight, it either goes up on one side or up on the other side. And so you push off on the ground, and it's a lot of fun. You go up and down and up and down, and it's a standard piece of playground equipment. And so here, if we take these masses and we take this distribution, and let's replace the support set with a board, right? And, this is just kind of an analogy to ground it out. And let's imagine this board was rigid enough that it could certainly support as much weight as you care to put on it. And so each value of the outcome for a random variable, our support set, represents a location on this board, okay? So let's now place some weights, some kettlebells, on this board, and the weight of the kettlebells are going to be directly the amount of probability mass at each location on the board. And so this is a kettlebell. It's a piece of gym equipment. It didn't exist when I was your age. And it looks like a cannonball with a handle on it, and they come in different weights, right? And you can do all sorts of exercises with them. They're very versatile. So let's then take our board with different locations over our support set, and let's put kettlebells at each location. And these kettlebells have a weight equal to the probability mass at that particular location. Okay. So now going to the seesaw example, let's put a pivot somewhere at one of the locations that a random variable can take on. Now, in this case, it's a discrete random variable. It can take on values that are countable. You can draw in one-to-one association with a set of natural numbers. But in the case of something that's a real numbered random variable outcome, you could place that pivot anywhere in any location along the board. Any questions? Does that make sense? Yeah. And so now, if we place the pivot at the one location corresponding to one heads in 3 flips, the board is going to drop on the right-hand side because the rotational force, the moments on each side of the board is not the same. And so when we compute this idea of the expectation mu, this probabilistic average, that location on the board is equivalent, in this case, to that placement, but more correctly, it's the placement such that the board balances. You have equal rotational forces on either side of the board. And this is often called the center of mass of a distribution. It's alternately called the location parameter for the distribution. And that location parameter or center of mass represents the notional center of all of the values that a particular random variable can take on. And so if you were to make a probabilistic or an educated guess, so to speak, over what values you're going to see if you try this experiment or run this system a large number of times, the safest guess you can have is the center value. So important is the center value that when you describe or summarize your distribution, this is considered the origin of the distribution, the center location, and all the other values or locations of your support set kind of spread themselves around this particular center. Okay. Any questions about this? Does that make sense? Yeah. And so it's called the center of mass. You'll see that all over the literature, or the so-called location parameter at a graduate level. All right. So another concern that we have is the variability, the so-called variance. And this represents how much the values of the support set are scattered about this support set or along that board. And so sometimes these values are very scattered to the left and to the right along the board. Sometimes they're very compactly scattered. And so it's important because if you're enterprising to guess what an outcome is for a random variable, if it's more dispersed or more widely spread out, it's going to be more difficult to guess that. If you were enterprising to use these types of measurements over, for example, securities, stock, something that varies more widely, you have an opportunity to get a really large return. Because if it varies very widely in its value, you know that if it's really low, small dollar value now, there's a very good chance that in the future, it's going to go very, very high. Okay. Any questions about this? Does that make sense? And so what we are concerned about with this variability or this dispersion, oh, that's an example. Totally, I'm forgetting about this slide. What we're concerned about is how broad it is. And so we have the center of the distribution, and we have this spread of the distribution. And again, center and spread or dispersion aren't the only two summaries that you can make about the distribution from its visual representation. And so here on the left, we have random variable big X, and that's the 3 coin flip system that we've been carrying forward over the last module. And then on the right-hand side, your right, we have random variable big Y. Now, imagine if you had a biased coin, meaning that the sides don't come out 50-50 heads or tails. You might get something like this for the random variable that measures the number of heads. And so when we calculated for the fair coin, we got 1/8, 3/8, 3/8, and 1/8 for our probabilities for 0 heads, 1, 2, and 3, respectively. But imagine, in this case, for our biased coin, we had the following, where the probability associated with each one of the counts, the outcome of this random variable y, number of heads, was equiprobable: 2/8, 2/8, 2/8, and 2/8. So to your question, right, in this case, we have two different measurements, x and y, and the difference between the x distribution and the distribution of random variable y is that the coin is different, right? Here we have a fair coin on the left. Here we have a biased coin on the right. And so if you were to gamble in one of these systems, on which one would you rather wager? Coin system X or coin system Y? Let me ask you that. X or Y? No one? X or Y? How about you? X or Y? Which one would you rather wager with? X? Y? Why do you think? Mm-hmm. Absolutely. Absolutely. Great. Thank you. And so, yes, it's harder to guess because there is equal probability. I'm just going to check my headset and make sure it's still plugged in. I disconnect if I get too far. Because they have equal probability, there are more ways to get it wrong. And so in the case of coin flip system X, guessing a 1 or guessing 2 heads is twice as likely as either guessing 0 heads or guessing 3 heads. If we look here, they're all equal. So if you make a choice of, say, outcome 1 heads in this flip of the coin 3 times, then we get 6/8 chance of getting it wrong. Okay, so the chances of getting it wrong is greater, and therefore it's much harder to guess. And so in the case of coin flip system X, we have what we call structure, right? It's not arbitrary, it's not random, it's not uniform. There's some structure there. And so if you were observing some game, you observe that game for some number of plays of the game, and then you compute this distribution, represent this distribution, and look for structures, right? Said differently, if the choice is different from arbitrary, then you use that information to advantage yourself on the ways, how many ways you can get it wrong. Okay? And any questions? No? And that's why in games of chance, the payout tends to be much bigger for games where there are more chances of getting it wrong. And so, yes, there's a physical aspect. So in something like roulette, you have a little marble or ball, and you have a wheel with, I forgot how many numbers. You roll the ball, and the chances of that ball getting in one of the spaces is pretty low versus other games. Okay. Any questions? No questions? No? Does that make sense? Yeah. All right. And so we use this information in other systems. It could be mechanical systems, it could be sensor-based systems, it could be typical, databases or customer purchase information. We can use this idea of finding structure in our systems probabilistically to advantage ourselves on what these values might be. Now, variance measures the dispersion, how spread out these measurements are. And some system that we saw in the coin flip system X and Y, we saw that when you have a lower variance, it's easier to make predictions about the data behavior of the system. And so that's because the probability mass, these kettlebells, are more scrunched together, more tightly packed. In the high variance case, we saw that with the coin flip system Y, the values are more dispersed, they're more spread out. Okay. And it's harder to predict because there are more ways to get it wrong, since more of the probability mass is further away from one another. Okay, any questions? Does that make sense? Yeah. All right. And so, how do you define this dispersion? When you say spread out, you have to define an anchor, a notional origin about which these kettlebells are spread out. And so it's often defined with respect to the center, that same probabilistic center, that mean that we talked about before. And so here, the variance is often summarized as Greek symbol sigma squared is our variance. And this variance is another type of probabilistic average. And so we have here sigma squared in functional form variance of random variable x. And every time we see with variance, whatever that parameter is to that function, it's going to appear in terms of the instantiation or outcome of the variable in the expansion, or it could be a function of the random variable. Either way, right? It's still variance. So you can say, what's the variance of the derivative of the heart rate? You could say, what's the variance of the heart rate itself? It's still variance. And so here we see the definition for the variance. It's a probabilistic average, an expectation. Expectation of what? The random variable or measurement x minus its expectation. And so we're going to replace this E of x here, that's the center that we talked about, with Greek symbol mu, and we square that. And the reason for squaring it is that we're concerned about the magnitude of that difference between a single measurement and the center of the distribution, but we don't care about whether it's less than or greater than the center. We don't care about the direction. Any questions? Does that make sense? Yeah? All right. And so here, if we expand it out, it's a summation. And so here we say little x, because that's the outcome of the random variable, minus mu, quantity squared, and we weight each such squared difference with the probability for that outcome, p of x. Okay. Any questions? No? And so here we have the outcome, we have the random variable's mean, and we care about the difference and not about the direction. We care about the magnitude here. But like many things in topics in mathematics, there are a lot of oops moments that happen. And so, yes, variance is the measure of dispersion. But the problem with variance is that it's kind of hard to understand what this measure of dispersion means relative to the outcome of the variable. So if you were to ask me, what's the temperature going to be like today? And I said, it's going to be 38 degrees and the dispersion is 100 degrees squared, right? 100 degrees squared, that doesn't really make sense. How do I compare that to what the temperature is? And so one of the issues with variance, if you evaluate the variance, the unit for the variable is going to be squared. And so for some security, some stock, if you're looking at, what's the variability for Apple stock yesterday, or Friday rather, for the trading window, if you said $100 squared, well, what does $100 squared mean, right? What does Fahrenheit, 100 degrees Fahrenheit squared mean? I don't know if I should bring my sweater or bring my jacket, right? And so the fix-up for this is, the so-called standard deviation. That oops moment said, yeah, variance is this measure of dispersion, how spread out that probability graph is, our visualization, but it doesn't allow us an intuition behind what this dispersion means. And so you divide the variance, you take the square root of the variance, and that square root of the variance is called the standard deviation. So standard deviation expresses for you dispersion, but it registers it in the same units as the variable of interest. So now if you said, what's the temperature going to be like today? If I said 38 degrees plus or minus 10 degrees, you say, aha, now I can compare it to the quantity of interest, this random variable, this measurement, and I can now understand what that dispersion really means. Okay, and so the fix-up for having these squared units for the variance measurement of dispersion is to take the square root, and that square root, our standard deviation, is called sigma. Sigma squared is the variance, sigma, which is the square root of sigma squared, is a standard deviation. Okay, any questions? No question? And then there's a special term reserved where the variance, if that variance is not a random variable, but a function of a random variable, we call the standard deviation the standard error. And we'll talk about that at another time in the semester. Okay. Any questions? Does that make sense? Yeah. All right. And so there's an interesting relationship between the center of the distribution, mu, and the standard deviation, square root of the variance, that relates the total amount of probability mass as a percentage with the distance covered above and below the center. And so here, if we take our mean mu, our so-called location parameter, and let's assume it was somewhere in the middle, and we go plus or minus one standard deviation, we would note that mu plus or minus 1 times sigma, our standard deviation, and that might trace from here to here, for example. That represents about 62, 64% of the total probability mass. If we were to go mu plus or minus 2 standard deviations from the center, that represents about 99.6 or so percentage of the total probability mass. And then if we go 1.96 standard deviations above and below the center, that represents 95% of the total probability mass, or 0.95 if you're going to express it per centum, right? So this last one on the bottom is special, 95%. Now, 95% in statistics is accepted as being statistically assured or guaranteed. Well, you might be thinking, gosh, well, why not 100%? Because nothing's ever 100%. Anytime you involve stochasticity or uncertainty, you're going to have that little fudge factor, that error. And so in statistics, when you say 95%, what you're saying is this is so-called statistically guaranteed. You never use 100% for that, and that's not accepted in the statistics community. And any questions about this? Does that make sense? And so when we talk about this idea of do these two things agree, so-called hypothesis testing, one of the things you use that idea of 95% probability mass is to quantify this idea of, is this typical? So imagine then, going back to the Holter monitor example, you want to know, does Mr. Jones's heart rate coincide with what is normal or baseline for either some cohort of the population or Mr. Jones's own heart rate? You collect a lot of heart rate samples, and then for all the new samples, you test it against this 95% idea. Okay, and we'll have an opportunity to talk about so-called confidence intervals and outlier rejection later on in the semester. Okay, and so this relationship between the amount of total probability mass, the center of the distribution, and the standard deviation is a really important construct because it's used for all sorts of wonderful applications. Okay. Any questions? Does that make sense? Yeah. All right. And so let's pivot then to this idea of samples, because when you get your data, you're gathering samples, and we're going to use that to motivate some other concepts that are really important from a statistical perspective. So a population is a set of all of the possible units of interest, and I use the term units of interest deliberately and not data, because data actually represents a measurement you're making over something. That measurement could be identity, meaning you don't perform in processing, or that measurement could represent a lot of very complex processing. And so using this idea of random variables mathematically fits what happens in practice. And it gets particularly interesting when you deal with sensors, so-called where the atoms meet the bits, because things are very messy, right? When you saw this idea of missing values, right, well, you replaced it with an average. But in the real world, there are very many opportunities for sensors to fail or to get anomalous readings. And so you still, as a data scientist or a machine learning practitioner, you still have to do something with it. Okay. And so a population, more formally, is a collection of all the possible units of interest. And let's take the example, for example, of the homeless population of Worcester. Now, Worcester, for all intents and purposes, it's not a very big city. Yes, it's the second largest city in Massachusetts, but it doesn't compare to New York City, Los Angeles, Phoenix, Arizona, Chicago, Illinois, many other locales across the country. And so you can think of this population, sort of make an educated guess. If you're one who works on homeless issues, you can try to think about a structure associated with the population. In this case, the example I'll carry is the homeless population in Worcester. And so let's imagine then this population, in this case, is a hierarchical population with non-overlapping subgroups. And let's imagine that this population was comprised of 4 different subgroups. You have the homeless veterans, you have homeless families, you have those who struggle with drug addiction, and you have the aged out foster kids. Now, that's a pretty big issue. When someone turns 18 in the foster care system, they're kind of dropped from it, but they're still not ready to be on their own. And so you find these 4 subgroups in the population. And in the real world, certainly you don't have these discrete subgroups. They are overlapping in some way. But we're going to assume in this example, they're non-overlapping because it makes it easier for our discussion. Okay. And so with these subgroups, suppose that there's some real world population or proportion rather that exists. And let's assume these proportions are 20% of the homeless are veterans, 15% are families, 30% are those that struggle with drug addiction, and let's assume 35% are foster kids. Now, let me ask you, do you know ground truth what the actual numbers are for Worcester? No? How about just Maine South and Worcester, small part of Worcester? No? It's impossible to know the truth, right? And so this idea of these numbers that govern some attribute of the population that has a name in problem stats, it's called a parameter. A parameter, more general, is a numerical characteristic of the population. And in this particular example, this parameter describes the proportion of these different demographics in this homeless population. Okay. Any questions about this? Make sense? Yeah. All right. And so in this case, I just made up the numbers, right? I don't really know ground truth, but somewhere floating out there are the real numbers. That's the good news. The bad news is you don't have access to it. Nobody does. You could spend several tens of millions of dollars dispersing caseworkers to try to come into contact with the homeless population. And you could do that for 5 years and you would never find everyone in the homeless population, right? You never. And so the question then, if you have these parameters, and these parameters, because they govern ground truth characteristics of the population, they're sometimes referred to as so-called population parameters. You don't have access to them. So what do you do, for example, if you want to conduct a study so that you can inform the mayor of Worcester about how to best dispense tax dollars to serve this population? What are you going to do? Okay. Well, the parameters exist and you don't know what they are. You never will. But you can certainly observe units from within this population and compute some function over those units that you so-called sample from the population. And so the whole reason for sampling is that the distribution won't tell you what its governing characteristics are, but it will certainly give you examples of members of this population if you ask it, right? And that ask is the sampling, and you compute some measurement or random variable over the samples. Okay. Any questions about this? Yeah, make sense? And so here, on purpose, you'll notice in each subgroup, I've drawn an individual in red. Now, when you produce your sample, it's really important when you design an experiment, right, or trial, it's really important how you compute your samples. Because if I asked, for example, sampled or contacted individuals that was only from the veteran subgroup, any statement that I make over that data, those random variable instantiations, is going to be grossly incorrect. And when I deploy those resources, it's not going to serve a large segment of the population. And so when you sample, it's really important to consider how you design the trials or the experiments that give you this data. Okay? All right. So you observe units from the population, and it's really important when you select them, you do so without preference. Now, when I say do so without preference for something as large as surveying the homeless population, well, some homeless hang out at the library. Some might be, roadway infrastructure. Some might be in shelters, all over the place. When you say without preference, it's easy to draw on the board here. But in the real world, you have to consider where they are because time and location impacts what segment of the population you're contacting. And so if you report your results, part of that reporting is how you designed your experiments. So if you ever see those things like US News and World Reports, click the link and actually read how they did the experiment. And then the discussion is whether you agree or disagree with the trial or the experiments that they conducted in order to get this data from which they're producing the report. Any questions? Does that make sense? Yeah. And so you sample, and when you sample, you get some individuals, and you do so without preference, because if you do so without preference, you're bound to suitably represent all of the cohorts that comprise your population of interest. Okay, so we do this sample, and in the real world, excuse me, with this homeless example, you contact some individuals, and then you measure something about them. You collect data, ask them questions, and then you compute a function over that data. That's where the random variable tie-in comes in. Now, when you collect or compute this function, you hope that this function is suitable enough that the statements you make about the individuals you contact, about your sample, is going to be representative of the larger underlying population whose parameters you don't know. You don't have access to them. They're hidden from you. And so more formally, a statistic is any function over a sample. And a statistic can be something complex, like the derivative, like entropy. It could be something very simple, like the number of heads, or even just the raw outcome. Okay. Any questions? Does that make sense? Yeah? All right. And so a statistic is any function over a sample. And you can ask, for example, in this case, what is your status? Are you a veteran? Are you an aged out foster child? Do you struggle with drug addiction, etc.? And so another statistic for something like the spaghetti meatballs with broccoli index, SMB index, another statistic could be the derivative. The derivative is the rate of change for subsequent measurements. You could do that with the heart rate. It doesn't have to be just things like the number of heads. And so when you compute this statistic, you hope that the statistic is stable enough, and I'll describe what stability means, to be representative of the underlying population. And now, any statement that you make about your statistic, if it's a suitable statistic, it's a stable statistic, it will apply well to the underlying population. Now, remember when I first learned this, I thought it was magical. And it kind of does seem kind of magical. And we'll have opportunity to see this for ourselves, I think on project 3 or 4. Can't remember which one. All right, any questions? Does that make sense? Yeah. And so here, in this example, imagine we sampled 1,000 homeless. And mathematically, we're going to represent X as a set of little x1, little x2, up to and including little x 1,000. And so here, the little x's represent the individuals. And the function in this example, we could ask for what are the number of veterans? What are the number of families? Now, this is from the samples. We're asking what your status is. What is your status? And then we're counting the total from that 1,000 many samples. Now, imagine we got these numbers. Now, we can use what we compute over our samples, these statistics, these functions, and we can use them to make a statement about the general population. But if you are just collecting this information from the library, that's going to be grossly out of sync with the ground truth because the homeless in Worcester don't just stay at the main branch of the library in town. Okay, any questions? Does that make sense? All right. And so with that, some more formalism. Anytime we talk about a parameter, sometimes they use the word parameter or population parameter. We use, in our case, theta, and theta can be a single parameter or can be a vector of parameters, these descriptive numbers describing attributes of the population. But when we type or write theta hat, that's a so-called estimator for a population parameter. And so what this estimate means, this hat means that it's a quote unquote reasonable substitute. And an estimator is nothing more than a statistic that has these desirable qualities of stability. And because it has these desirable qualities of stability, it's a reasonable replacement for this unknown population parameter that you don't have access to. Okay, any questions? That makes sense? Yeah? All right. And so here, we take our samples, and floating out there in the population are the ground truth parameters, theta 1, theta 2, theta 3, and theta 4, which are the proportions ground truth for these various cohorts that comprise the homeless population of Worcester. And then we take our samples and we compute from that our proportions, our statistic, and we compute theta 1 hat, theta 2 hat, theta 3 hat, and theta 4 hat from our samples. Okay, any questions? No? All right. And so here, if we had the following counts from these statistics, we would then go ahead and for the veterans, we'd have 20%, families 30%, drug addicted 10%, and aged out foster kids 40%. Hopefully that adds to 100, right? I didn't make that typo, did I? 50, yeah, 50, okay. Any questions? And so we don't have access to the ground truth parameters or the population parameters, but we do have access to the estimators. And so the whole reason for statistics, in this class at least, and my stochastic computing class, I hope I get to teach that again soon, you are using what you know from your data, our estimators, as proxies for the unknowns, which are the population parameters. Any questions? Now, of course, this saves time, money, and effort. Because if you are conducting studies for something like the city of Worcester, you want to spend more of those dollars towards the programs to help people who are underserved in this case, and not on the study, right? So you decide how many is a reasonable number of samples to take, people to contact, what statistics are you going to use to compute your estimators? Are these things stable? And if they're stable, and we'll talk about what stability means, then they're good replacements and you can be guaranteed or have a reasonable amount of confidence that what you say about the samples will apply well to this unknown population parameter. Any questions? That makes, yes. An extreme outlier, you can actually detect and label those outliers if you know certain things about the data. And using this idea of standard deviation, that dispersion, you can literally reject outliers. So you can take your data, compute your standard deviation, and then iterate through your data and you say, are you this 95%? Are you this 95%? If yes, you're considered typical. If not, you're considered atypical, and you just exclude it from consideration. So you can literally reject these abnormal, I don't want to use that word, these atypical values that you measure using this relationship between the standard deviation and the percentage probability mass. And we'll have a chance to look at that. And we can do that in two different ways, which I won't talk about at this moment because we're not ready to, we haven't introduced that stuff yet. Okay? Any other questions? Other questions? All right. And so we deal with this. And as I said, every statement that you make about these estimators, it applies very well to the original population. And I think that's pretty amazing. I get excited about that. All right. Any questions? No? All right. And so here's an example about more complex data. We talked about random variables, and this photograph is from the 150th anniversary celebration of the Golden Labrador, Golden Retriever dog breed. And this is in the Highlands of Scotland. I guess there's an enthusiast group. There's something for everybody. And so let's consider this population of yellow labs. Now, if we look at these dogs, one of the ways you might describe a yellow lab or any dog breed is by its length, by its width, its height, its weight, as well as an attribute about its coat. Its coat, for example, is categorical. It can be shaggy, medium, can be smooth, all these variations. And so objects in the world carry multiple descriptors. And you can think of each descriptor as a measurement over the raw observation. The raw observation is some particular dog selected from a large population of that particular dog breed. It gets even more interesting if we consider every dog breed, right? And so for the yellow labs, we have our different measurements, and each dog in table form is represented as a row. And then each column is one of these measurements. And so collectively, the set of measurements together uniquely describes a particular individual sampled from the population, this population of yellow labs. So objects in the real world carry multiple descriptors, and how you express those descriptors is by a measurement. And mathematically, that measurement is in the framework of random variables, which is why we have them. All right, any questions? No. And so here, let's sort of abbreviate these random variables. Our first column, length, is L, with W, height H, weight M for max instead of W, because we already have a W, and coat is C. Now we have mixed variables here, and the unique co-occurrence of a particular value for each of these variables is what it means to represent a particular dog, a particular individual sampled from this population. And so this co-occurrence is not random, right? A random coat and a random weight and height and all these other measurement outcomes, they're not random because there's a particular association between these values that defines what it means to be a yellow lab. Absolutely, there's some variation, but it's not random. A different association might be a pug or German Shepherd or some other breed of dog. And so this idea about structure in your distribution is really, really important in understanding the behavior of the system that gave rise to the population. And so when we alluded to this idea of structure for the 3 coin flip experiment, when you deal with multivariate distributions, our structure is something you need to uncover. And you do that by examining the relationship between these individual variables or these individual measurements. That's really, really important. Okay, any questions? Does that make sense? We have about 8 minutes. And so here, the rows are the objects and the columns are the variables. And so here, dog 1 might be 38.5 inches, 18.2 inches width, etc. Right? So that represents dog 1. And dog 1 is just how we enumerate them because you need to identify them, right? It's not, here's dog 1, and the next dog born is dog 2, and so forth. That's not what this notation refers to. All right. And so here, if we were to generally describe what a particular dog is, the ith dog, that's just a vector of these random variables. And so one of the things we'll discuss at a later time this semester is so-called multivariate distributions. We dealt with single variables for coin flip system, random variable X from before, but now we have an instantiation of vector of these random variables. And so when we talk about the probability over vectors, we look at the probability of the vector of random variables taking on instantiations of those variables. And so here we'd have lowercase l, lowercase w, lowercase h, lowercase m, lowercase c represents an instantiation of these variables. Any questions? Does that make sense? Okay. And so underneath the covers for this instantiation, there's a distribution floating out there with parameters, and it's up to you to determine what those parameters are and use statistics for that. And part of those statistics, your analysis, includes examining the variable linkages, right? If I increase the weight by some unit step, how does the coat change or the height change or other things, okay? Now, of course, I use this framing example but it's not always so straightforward a priori for an arbitrary data set. Okay. All right. Any questions? Does that make sense? Yes. Mm-hmm. Great question. With a categorical variable, you assume they're equiprobable unless the data tells you differently. And so you get your samples and you could just choose to have them have equal probability random, or you could literally just count the number of occurrences and assume the that is indicative of how the population behaves. Okay. Any other questions? No? Make sense? Okay. So a yellow lab is not a random co-occurrence of these instantiations, right? You have certain linkages between variables about what it means to be, in particular, a yellow lab. And in fact, so important are these co-occurrences in disciplines like computer vision, you can actually describe the content of images by looking at the co-occurrences of certain colors and certain relationships in an image library. Okay, any questions? No? All right. And so one of the key questions that you enterprise to ask as part of your analysis when you're dealing with multivariate data is, how do our variables behave? Does an increase in one value come along with a decrease, no change, or an increase in another variable? And if this linkage is very strong, you can actually uncover better how these systems behave. And that's really important for things like supply chain analysis. Now, it's obvious to know that gasoline, right, is derived from oil. So if the cost of oil goes up, so too does the cost of gas. But if you didn't know what those linkages are, you have to evaluate them. And based on those results, pose your model assumptions from that. Okay. And so it's really important, and people aren't generally in the beginning comfortable with it, that you have to accept the unknown, right? There might be linkages that are not obvious, and these linkages might be one level of indirection, meaning variable A is linked to variable B. It could be more than one level of indirection. When variable A does this, it causes variable B to do that, and variable C will therefore do the following, right? And so it's not always clear how the value of your data arises. And in practice, there's some distribution that governs the value. And these linkages are known, as well as the parameters that define the distribution. You have floating out there all the possible values, but you don't have access in some cases to all the possible values. Okay. And so this is truly experimental, because where your analyses along the way will shape what analyses you apply further in order to extract the insights from your underlying data. Okay. Any questions? That makes sense? So we have about 4 more minutes. And so here, when we think about our population, in the case of multivariate or vector valued data, we have our population, and this distribution describing our population is giving you data. Now, in this case, you don't have control over what it gives you, right? A dog is a dog. Maybe you could go to different parts of the world. Maybe you could, ask people, but you don't have control over what it gives you in this case. With the homeless population, you have some semblance of control, because you could certainly go to different locations and choose different times when you believe homeless will congregate, okay? And so with some types of systems, you just kind of get what you get. And the question is then, how many samples do you need in order to properly make the statements that you hope will be statistics that are consistent with the underlying population? And so there are some analyses that look at the so-called power of a statistic. And what you're looking at is the sample size reasonable so that your errors, your variability will pay for the statements that you're trying to make. Okay. Any questions? No? All right. And so here, dog 2, you're given that one, you're given that one, you're given that one, you're given that one. When do you stop? That's another question. How big should your sample size be? All right. Any questions? No? All right. And so this idea of the relationship between the samples, the statistics, and the types of insights you can extract from your data, you start with your population. You don't know the characteristics or the parameters that govern your population, but you can ask your population for examples, and those are your samples. And the important part is how you choose to direct your samples. In some cases, you might have a particular budget associated with your samples. If you're going to contact the homeless population, it costs you money as a municipality to pay those caseworkers who are going to go out and try to find them. And so if you have a finite budget, placing your samples appropriately so that the statistics you compute are stable and well representative of the underlying population is a really challenging problem. And so in certain disciplines like social work and urban management, what's it called? Urban planning, you take courses like experimental design, because the considerations about how you conduct studies in order to get data is very, very tricky, especially in light of finite budget resources. Okay. So then you take your samples, and from that you compute functions or statistics, and you do your analyses on the statistics for stability. And if they are quote unquote stable, then any statement you make about these statistics will apply well to the population, so much so that you can use the statistic as a replacement for the unknown population parameter. And then given that, what can you do? If you can model or mimic this distribution that produces this data, now you can ask your model questions, and you can effectively create artificial individuals, and then you compute other analyses over those artificial individuals. And so if I had enough measurements of yellow labs, I could compute a distribution, I could compute my statistics, replace those estimators for those in those models, and then now create artificial dogs, and then answer all sorts of questions. This idea of creating these artificial individuals and computing things over them, that's called inference. And there's a lot of interesting work in inference. That's where you're doing the forecasting, and that's when you're trying to project and predict how the behavior of the underlying system might play out, even though you haven't physically gone out and collected new samples. Okay, any questions about this? And we'll have a chance to do inference. And in fact, for customer recommendation, that's directly an application of a type of inference, right? And we'll have a chance to do a little bit of simple recommendation and an example towards the end of the semester. Okay, any questions? No? All right, so that's right about time. We have 2 minutes left. So I'm gonna end there, and we'll pick back up on Friday with this material. But on Wednesday, we'll pivot to the practical stuff. We'll look at Jupyter notebooks and some visualization APIs. Okay? All right, so have a great week. Happy Monday, and I'll see you all on Wednesday.